Okay, so in the previous video, we talked about the steps required to draw your titration curve for the amino acid cysteine. So I thought that it would be a good idea to now put everything together and kind of conceptually go about understanding what the titration curve shows you, where the buffer region is, and all that stuff, because I think having this conceptual background helps answer a lot of like your study questions, and I think it's very useful. So let's just first reorient ourselves. Again, we needed 3 equivalents of NaOH because in order to fully deprotonate our amino acid cysteine from the fully protonated form shown over here, you need to add 3 equivalents so that you can go to the fully deprotonated form over here. Then we went to our half equivalence marks and we plotted our pKa. And again, where the pH equals to the pKa, you have a 50-50 mix or a 1-to-1 ratio of your weak acid to conjugate base. So for example, where my pH equals to my pKa of 2.0, that means I'm going to get a 50-50 mix of the weak acid to conjugate base. Okay, we're going to get a 50-50 mix over there. Same thing if I was at a pH of 8.2, I would get a 50-50 mix of this thiol group in its protonated form as our weak acid, and then the deprotonated form as our conjugate base. And then same thing at a pH of 9.5, you get the weak acid conjugate base for the amino group. Okay, so the idea here is now I want to try to understand what's going on as we're going through our titration curve and trying to see if we can, come up with some conclusions about our buffering region, okay? So what happens is as we're going across our titration curve from left to right, what we're doing is we're adding NaOH, and what NaOH is doing is it's effectively deprotonating our amino acid, okay? Now, let me ask you guys this question. What did we say was the definition of a perfect buffer? We said that the perfect buffer, the idea behind it is that it has a 1-to-1 ratio of your weak acid to conjugate base. So no matter if I add strong acid or strong base, it'll be able to resist changes to your pH. So if I was going to tell you guys where you would find that on your titration curve, well, think about it like this. On our titration curve, if we start at our leftmost point over here at the 0 mark, before I added NaOH and I'm at a pH of roughly 0, that means that my amino acid at that very, very acidic pH, everything that can be protonated will be already protonated. So now if I wanted to get a 50-50 mix of my weak acid to my conjugate base of my carboxyl group, so the first thing that's going to get deprotonated is my carboxyl group because it has the lowest pKa and it's the most acidic. So now if I wanted to get a 50-50 mix of the COH to the CO minus, what I'm going to do is I'm going to add half an equivalence. And if you don't understand the idea of equivalence, there's another video on that. But the idea here is that if you add half an equivalence, all that means is that you're adding half the amount that of the amino acid that you have. So that means that in this case, if I had half an equivalence, I would deprotonate 50% of my COHs to make it 50-50 of weak acid to conjugate base. And we said that at the perfect buffering region, we are going to be able to resist changes to pH. And then notice how when we're in this buffering region, as we're going across this, because remember, this axis is showing us that we're adding more NaOH, as we're going across over here, notice how the pH is not really changing. Because again, we have that perfect buffer, okay? And anything around that is in our good buffering region, and that's why the pH is not really changing. But then, I want you to notice at the full equivalence point, when we get to that full equivalence point, notice how the pH drastically changes over here. The idea here is that once we're at our equivalence point, remember, if I added one equivalence of NaOH, that means I fully deprotonated my weak acid, and now I only have my conjugate base, meaning that 100% of my molecules in solution look like this at my equivalence point. Okay, so that means that I don't have an appreciable amount of weak acid to conjugate base, so that I don't have a good buffer, and that means because I don't have a good buffer, I'm not going to be able to resist changes to my pH, and that's why my pH changes drastically at each of my equivalence points, okay? And then notice how at my half equivalence points, they stay relatively constant. Now, this is all fine and dandy. The reason why I made this video is I wanted to go over an extra concept which I think will help you answer a few of your study questions which involve buffers. It's specifically for the one about Steve's buffer or something like that. I think this understanding the titration curve like this will help you understand what's going on. So I know how previously we said that a good buffer, we said that it needs so a perfect buffer is a 1-to-1 ratio. A good buffer, we can have a 10-to-1 or a 1-to-10 ratio, right? We said that as long as it's 1-to-10 or 10-to-1, and then by the Henderson-Hasselbalch equation, that's a plus or minus 1 of our pKa, we have a good buffer. So if I drew in my buffering regions for these different functional groups, it's plus or minus 1 of my pKa, meaning that if my pKa is 2.0, it will be 1 to 3. Then this one will be 7.2 to 9.2. And then this one will be, I cannot see, 8.5 to 10.5. And we already knew this, that it's plus or minus 1 of the pKa. And again, go to the Henderson-Hasselbalch equation if you don't know how to get to these values. Okay, but the additional thing I want to talk about is how we can talk about our buffering region in terms of our x-axis, because right now I just showed you the buffering region in terms of the y-axis. I think it'll help to understand in terms of the x-axis. Okay, so now what I'm going to do over here is I'm going to ask you guys a question. So what did we say the beginning of a good buffering region was? So what, in terms of like ratio or percentages, let's talk about percentages. What did we say was the ratio of weak acid to conjugate base we need for the edge of our good buffering region? Well, if you remember, we said that it was a 10-to-1 ratio of weak acid to conjugate base is the start of our good buffering region. And if we translate that into percentages, that would mean that if we wanted a good buffer, we will want 90% HA to 10% A minus. So we said that that's the edge of our good buffering region in terms of on the first side. So if I think it's actually more helpful if I drew it out a little bit more straightened out like this. So if I drew it out like this, we said that the perfect buffer is when we have a 50-50 mix. Okay, the edge of a good buffering region over here is 9 to 10, and then the other side is 10 to 90. And these are again HA to A minus. And this happens again for every functional group. So now let me ask you this question. So if we're talking about how can we get from 100% to 0%, so how do we get from here to that? From here to there. So how do we get from our equivalence point? Because remember, our equivalence point is 100% only one species. So how do we get from that 100% to the 90%? Well, remember, if we add one equivalent, we go from 100% to 0%, because an equivalent just means we depronate all of it. An equivalent is an equal amount. So one equivalent will get us from one side to the other. Half an equivalent will get us from one side to halfway through. So if I add 0.1 of an equivalence, right? Remember, half an equivalent will get us, or half, which is the same thing as 0.5, will get us here. 1 will get us here. So to get us here, we need 0.1 of an equivalent, because if we added 0.1 of equivalent, I would deprotonate 10% of my weak acid to form 90% weak acid and 10% conjugate base. Okay, so the idea here is that the edge of my good buffering region starts at the 0.1 equivalence. So if I go over here and draw in the edge of my buffering region for my x-axis, it starts at 0.1 equivalence, because that's how I'm going to get my 90 to 10 ratio. Okay, now on the flip side, if I wanted to get to that 10 to 90 ratio, how many equivalents do you think we would need to get to right over here? Well, again, if we needed one equivalent to get all the way over here, we would need 0.9 equivalents to deprotonate 90% of our weak acid, so that we only have 10% that remain protonated. Okay, so that means that if I wanted to draw it out over here, my other side of my buffering region is 0.9. So a key takeaway here is that my buffering region is from 0.1 to 0.9 on the x-axis, and it's plus or minus 1 of the pKa on the y-axis. So every 0.1 to 0.9, so 1.1 to 1.9, 2.1 to 2.9, and it goes on forever. Every 0.1 to 0.9 is it's the start of your buffering region, because that's how once you add 0.1 of an equivalence, that's where you get your 90 to 10 ratio. Okay, so now I just wanted to, so that was the basic idea of what I want to convey to you guys, but I also wanted to go one step further, and I think this kind of puts everything quite nicely together. So I'm gonna basically, what I'm gonna do is I'm going to zoom in to this region of my curve. Okay, I'm gonna just draw it a little bit bigger so that you guys can see what's going on. Okay, so here's again where my half equivalence point is. So it's 0.5. This is my full equivalence. And we said that our buffering region starts at 0.1 and this ends at 0.9. And again, notice how this is such a large buffering region. It goes all the way from 0.1 to 0.9. So when I'm not in my buffering region, it's only in this tiny area of 0.9 to 1.1 and then 1.9 to 2.1. So the buffer region is actually a very, very large area that is able to resist changes to pH. So it's a very tiny area where you're going to see those drastic changes to your pH, and it's near your equivalence point. Okay, but now going back to this. So I said that, and I'm going to draw both buffering regions. So it's plus or minus 1 of the pKa. So the pKa was 2.0. This is then plus or minus 1 is 1 to 3. So now what I want you guys to understand is, well, think about it like this. I want to connect the buffering regions of the x-axis to the buffering region of the y-axis. Well, let's think about it like this. When the pH is equal to the pKa, that means I am at my half equivalence point. So this region right here corresponds to this region over here. Now, let me ask you this question. If I go back to my illustration over here, and I want to say that I'm going from, I just want to get to the beginning of my good buffering region. So I added 0.1 of an equivalence. Well, if I add 0.1 of an equivalence, that means I'm going to get that 90 to 10 ratio, or that 10 to 1 ratio of weak acid conjugate base. And when I have a 10 to 1 ratio of weak acid conjugate base, what will my pH be in relation to my pKa? Well, remember, if we go back to that Henderson-Hasselbalch equation, and I'm just going to quickly do this. Remember, if I wanted to get my 10 to 1 ratio, all I'm going to do again, let's just make the pH 1 equal to pH 2, and I plug in over here. I subtract 2 from both sides, that's equal to negative 1 log of A minus over HA. 10 to the power of 1 to get rid of it. Okay, so 10 to the power of 1 is the same thing as 1 over 10, A minus over HA. So notice how I got that 1 to 10 ratio when I am 1 unit under my pKa, which is the same thing when I add 0.1 of an equivalent. So effectively what I can say, and this is the connection here, is that this, remember, the lower end of my buffering region corresponds to 0.1 equivalents, okay? And if you do the same thing and you plug into the Henderson-Hasselbalch equation and you get plus 1 of the pKa, you're going to get 10 to the, instead of 10 to the power of negative 1, you're going to get a positive 1. So you're going to get 10 over 1. So instead you're going to have a ratio of this when you're 1 over your pKa. And the idea here is that you're going to be corresponding to this region right over here, which means that this top buffering region right over here corresponds to the 0.9 mark. So I think under